This final short video is just a little bit of a warning about the way the Fourier transform is defined and the kinds of things you're likely to see if you're looking at other materials about the Fourier transform. The problem is there's a factor of 2 pi you've got to put somewhere when you're doing a Fourier transform, and depending on where it ends up, you can end up with quite a few different versions of the Fourier transform. And you'll see these when you look at other books and other materials online. You'll see the Fourier transform defined in different ways. It's all the same Fourier transform, it's just a bit of a technicality you've got to look out for. And if you're using Mathematica to look at Fourier transforms, it's also critical to remember this, because if you want to get the Fourier transforms that we've defined in these videos, you've got to tell Mathematica what you want explicitly. So the Fourier transform we're using Mathematica is defined using this command here, Fourier parameters 1 minus 1. If you want to see what that means, then just look at this link here. And this gives us the Fourier transform defined in this way as we've done in the videos. So for example, if I take the Fourier transform of the cosine of omega naught times t, I would do it like this. The command is Fourier transform. This is the real space variable. This is the frequency variable. And I give it this command, Fourier parameters 1 minus 1. And that gives me the correct Fourier transform. And the answer is pi times the Dirac delta function at plus omega naught and minus omega naught. You could also define it as minus 1, 1, like this, and that would be backwards to our version. That would give us the Ford transform with a factor of 2 pi here, and a plus I here instead of a minus, and here the factor of 2 pi has gone away and we've got a minus. The default Mathematica Fourier transform is given with Fourier parameters 0, 1. So if you leave this command out here, if you leave this option out altogether, this is what it defaults to. And this is symmetric, so it's got a factor of 1 over root 2 pi in the forward and reverse transforms, and it's a plus ik and negative ik, so the opposite of what we use. And finally, one that's also very commonly used is the Fourier parameters 0 minus 2 pi. So here we've got the negative sign in the forward transform and positive in the reverse, and the factor of 2 pi is taken up into the exponent here, and there's no factor of 2 pi that appears in front of the transform. So, as I say, the Fourier transform comes in really too many flavors, and this is just a little bit of an instruction how to do the Fourier transform using Mathematica and how you get the answer you expect. And finally, it may come as something of a relief to know that very rarely will you ever have to compute a Fourier transform by hand. Pretty much the whole time you can refer to a table like this, and that will be enough for the purpose of this course and probably for the rest of your physics career, unless you do something very unusual, because there are actually a fairly limited number of functions that you ever really care about, as it turns out. So here are some functions in real space, and here is the corresponding Fourier transform. I've written it down in terms of time and angular frequency omega, but if you replace t with x and omega with k, you get the Fourier transforms in spatial coordinates.